Now, once again, in the theoretical distribution, see what we get from our experiments are experimental data. And it happens almost all the time that we try to figure out if there is a theoretical distribution, probability distribution available, which either describes or does not describe the data. I mean, we have specific purposes. If it describes, then we can get some information. If it does not, even then we can infer some other things. So it is always a practice for an experimentalist after obtaining the data to figure out if it corresponds to, if it matches with, if it looks like some theoretical distributions. And here comes the concept of probability distributions. So now what is that? What is distribution? So let us start with a problem which I think all of you have encountered at some point of your professional life, starting from your high school days till now. We all, I mean, we have come to this in our childhood. In the playground, we make a toss. So that's why I call it the age-old problem with the coins. I mean, problem or solution, whatever it gives us. So let us toss, let's take 4 coins. I mean, we all know that if you toss a coin, and if you do that for sufficient time, sufficient instances, then the probability of getting either the head or the tail is half. So, and we also know that, I mean, if you toss a coin once, then you can get either the head or the tail. But if you toss it 3 or 4 times, this probability does not come to be half. But if you do that for sufficiently large number of times, you really go close to the half, close to the number half. So let us, for this discussion of origin of distribution, let us take 4 coins and toss them, okay? And we all know that the probability of getting either head or tail is half. The first thing, let us consider that all 4 coins can give head, right? As I said, that if you just take 4 coins and each of them has a probability of giving you head or tail, but it can so happen that all 4 coins can give you head, right? But then the probability of that if you take 4 coins and toss them, all 4 will give head, is given by half to the power 4. That you all know, that you just multiply each of the probabilities and you get the total probability, which is 1/16. This is very simple. What happens if we ask for 3 heads and a tail? You can ask for 3 heads and a tail. So then you see each coin has a probability of half. Okay, so then you can multiply them, and then you get a set of probability of getting this is 1/16. But then you can have 4 type of arrangements which can give you 3 heads and a tail, because you can have head, 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 and tail, or you can have head, head, tail, head, or you can have head, tail, head, head, like this. You can have 4 combinations. So if you take these 4 combinations, and for each one you get a probability of 1/16, then you get the total probability 1/4. You can have other possibilities too. For 3 tails and a head, okay? For 3 tails and a head, the probability will be the same as the just above one. That the 3 heads and a tail and 3 tails and a head, they have the same probability, because you can have same combination, same probability for each combination, then you multiply, you get 1/4. Okay. But if you take a different case, like two heads and a tail, then you can have, once again, you have the probability of each one is 1 over half, and then one half to the power 4 is 1/16th is the total probability. And then, but to get two heads and two tails, there's a mistake here. This is, sorry. Yeah, this is two heads and two tails. That you have 4 points. Just correct this here. I'll correct it in the lecture note later on. You can have 6 combinations like that, 6 type of combinations. So head, tail, tail, head, tail, tail, head, tail, like that. You can make 6 combinations, and the total probability comes out to be. Then, similarly, if you take just the other side of the first combination, you can have no heads and 1 tail. The first one was this, like this, so you get 1/16, okay, like that. So you can have all of these type of combinations, like 5 combinations. Okay, we all know that the total probability of all these combinations can be calculated. Let us do that. Let's check what is the total probability. So total probability is given by sum over ER. R is we call it a success here, or then the R is the running index, which runs for all combinations. So then you just multiply add, take a sum of P0, P1, P2, P3, and P4. So all 5 combinations, and you get it 1. And that's what we all know, that the total probability of anything has to be 1, right? Because for a coin also, you get a is half, probability of getting tail is half, so the total probability is 1. Here also, it is the same thing. So we did not do anything wrong. So the probability of getting R heads from tossing 4 unbiased coins is given by PR. You can write this in this way, that the probability of getting R heads, R can have 0 heads, 1 head, 2 heads, 3 heads, and 4 heads. Okay, you can write it like this: 1/16, 1/4, 3/8, 1/4, and 1/16. So this is what is called a probability distribution. Got it? We started. So it's just the simplest example. You take a coin, toss it, you have probability of getting 1 head or 1 tail half. Then you can have, just to give you an idea of what is a probability distribution, I took 4 coins and tossed them, and you can have these many combinations and these many probabilities, and you can write this as a probability distribution. This is the basic probability distribution of getting 1 head with 4 coins is like this. If you take more number of coins, you just have more elements here, but you can still write it like this, and you can still calculate and you can see that the total probability will always be 1. Okay, so this is the fundamental probability distribution, so to say. What is the expectation value? Okay, what is the expectation value of this? That can be calculated. We know that the expectation value of R is given by sum over RER. Okay. Let's see what happens with the average number of heads with the coin. So we all know that the expectation value is this. But let's see whether it comes out to be like that or not. Okay. So this is R and this is PR, right? So if you put the value of R0, that is, you don't get any head, you have the probability 1/16. You get one head, you have the probability of 1/4. You get two heads. For that, the probability is 3/8. If you want three heads and one tail, you have the probability of 1/4. And if you ask for all four heads, you have the probability 1/16. If you take this, if you multiply and take a sum, it is 2, right? And the expectation value of R is really 2, because you can have two things, right? That is what is the expectation value. For any function, similarly, for any function R, function of R, so we started with R, the expectation value is defined in the same way. That is, expectation value of FR is FR multiplied by PR, take the sum over R. Okay. But then, is this the same as average of a data sample? In the previous lecture, we discussed about a data sample having many elements, and we took average. So is this expectation value same as the data sample? Expectation value is the sum over a theoretical probability distribution. This is exactly what we derived. This is exactly what we got if we take these two coins. That is a theoretical probability distribution. And the sum over a theoretical probability distribution, I omitted this, but this is in purpose. Okay. The sum, when I say sum means that the probability, the expectation value of a quantity is multiplied with the probability distribution, and then the sum is taken. That is the way to say sum here. It's not only the sum of the probability distribution. However, the average is the similar sum over a real data sample. So this is where is the difference. If we deal with theoretical probability distribution, we always talk about expectation value. However, when we deal with real data sample, we always talk about average or mean, not the expectation value. So when you deal with two different things, be careful, be cautious to call what you are calling. Okay, if you are dealing with theoretical probability distribution, don't talk about average or mean. It is the expectation value. And when you are dealing with real data sample, it is always the average. If the data sample follows a theoretical distribution, then as the size of the sample tends to infinity, now these two are coming closer. So if you have n number of samples, n number of data, where n tends to infinity, if you have very large number of data, in that case, you can interchange this, okay? Or you can say the expectation, you stop calling it an expectation value, you start calling it an average or mean, okay? So you can do this only when you have a very large number, infinitesimally large number of data samples, okay? In that case, you don't call it expectation value anymore, you start calling it the mean or the average. Okay. Now, when you have large number of data, large amount of data sample, you introduce another quantity which is called the probability density distributions. Why is it called so? You will realize we may end up with measurements resulting in values within a range. So here comes, we in the beginning of yesterday's lecture, we told something like binned data. So when you have very large number of data in a range, then sometimes you have to bin those data and make small bins, and then calculate other quantities like the central tendencies, like the average or spread, etc. So here we say that the probability that the measured value of x may lie within x1 and x2. These are the two ends of the beam. Then the probability that it lies within this range is defined as p equals to integral x1 to x2 px dx. This is how it is defined. Here, the px is called the probability density distribution. It is like, why it is called the density distribution? You know what is density? It's mass over volume. So that is, the mass is the quantity, the entire quantity, and volume is a defined content, right? So like this, here your data sample is the total data sample, and this is the range. So it is somewhat analogous to the term density, and that is why it is called probability density distribution. Okay, so the probabilities are numbers, right? Probability, we had the example of the coin tossing. Those were probabilities. You have number of 1 by 16, 1 by 2, 1 by 4, 3 by 8. Those are probabilities. Those are numbers. But the probability densities have dimension of inverse of the quantity x. Okay. Okay, because this is the probability. You see the dimensional analysis. This is the probability, which is a number. Here, this is the probability density, which has the dimension of inverse of quantity x, and dx has a dimension of x. So the dimensions cancel out to get a number. And that is why the probability densities have the dimension of inverse of the quantity x. X can be anything. So x is just a general nomenclature. X can be anything, but always keep in mind that the probability density have the dimension of inverse of the quantity x. Okay. With this new idea of the probability density distribution, we can now define again the center tendencies like the mean, the mu, it is called mu, equal to the expectation value. You can say the expectation value for data samples. That is integral of minus infinite to plus infinity x px dx. Okay, so you are taking the entire range. Okay, you are free to do a range division, but here if you have to calculate the central value, which is the average, you have to take the entire data sample, whatever is available to you. That is why we have taken a general integral minus infinity to plus infinity x px dx. Okay. You see, once again, the dimension matches because this has the dimension of x. This is the dimension of x. This is inverse of x. This is once again x. So this px dx is a number, and x has a dimension of course, x. So the dimension in two sides matches. And similarly, for fx, if we have a function of x, you can calculate the expectation value as fx px dx. Okay. So this is the introduction of the probability density. Now, with this introduction, we come to the real theoretical distributions. And once again, there are two types of distributions. One is discrete distribution, so to say, which deals with discrete numbers. And the other type of distribution is called continuous distribution, which deals with very small numbers, very closely apart numbers. So those numbers are so close that you cannot deal with only integers. So you can have continuous distribution. So three types of distributions we will discuss. And the first one is the binomial distribution. What is a binomial distribution? Which describes the processes. I hope I am audible because I don't hear anything on the other side.
Yes, sir, you are audible.
You are audible.
Thank you. This Binomial distribution is a distribution which describes the process that can have two different outcomes. The most familiar example is a coin. Well, there can be other examples too, like quality checks of products, where if you are a quality checker, you take a product, you make a new iPhone, you check it, I'd say either this is okay for going to be in the market or not. Okay, so QC pass or QC fail. Like for a coin, you can have a head or tail. A QC for a product can have pass or fail. Okay, well, I mean, in some cases, the QC can be other can have other values like a small repairment or refurbishing or something like that. But then at some point, it has to pass. So there is a pass or fail to make it a sellable quantity. Or if you are a football fanatic, a result of a penalty kick, it can either be a goal or not. So there cannot be any other result, right? It can either be a goal or not. So if you have two different outcomes for a process, then you can call for the binomial distribution. The probability of success, for example, for a coin, you can say head is a success. For a quality check, you can of course say pass is a success. And for a penalty kick, you can say scoring goal is a success. Is P. The probability of success is P. And that of failure is 1 by P. Sometimes people write it as Q, but then you have another variable. Here you can deal with only P. So you can say 1 minus P because your total probability is 1. So if the probability of success is P, then the probability of failure must be 1 minus P because you can have only two types, two outcomes. If one makes n number of trials, like we made 4 trials with 4 coins, you can make n number of trials. Okay, so each of which having individual probability of success, right? For example, if you take 10 shots in a goal for penalty kick, each time you can have a probability of success P, right? You can have a probability of success. It can either be a goal or not. So you can have a probability P of success. Okay. This distribution, this binomial distribution gives the probability of R successes. Okay. So for n number of trials, each of which has an individual probability of success P, the binomial distribution gives the probability of R number of successes. Okay. How you do that? How you get to that? There are two factors which constitute the distribution function. The first one is 2 to the power n possible permutations of success and failure. You can have either success or failure, so 2. For n trials, you can have 2 to the power n possible permutations of success and failure, of which you can have R successes in this number of ways. That is NCR. You can have R combinations, NCR combinations, which is n factorial over R factorial into n minus R factorial. And then the second factor is R successes of probability P and n minus R failures. R success and n minus R failures of probability 1 minus P, because you have the probability of success is P, you have probability of failure is 1 minus P. So you can have R success of probability P and n minus R is failure, but that comes from probability 1 minus P, which combines the probability, the total probability of these two is P to the R 1 minus P n to the R, n minus R, right? You can have R successes of probability P by P to the R. You remember you had half from a coin, you had half the probability of getting head. So if you take 4 coins, you had half to the power 4. So exactly like that, here you have P to the power R. And if you have a probability of failure 1 minus p, definitely for n minus r trials, because r has got success, so n minus r trial is left for failure, you have the probability 1 minus p to the power n minus 1 minus p to the power n minus r. Then the probability of r successes out of n trials, each of which has a probability of success p, which is written in this notation, p within first bracket r, that is the number of successes, semicolon p comma n, that you have p success p probability, and the total number, it's n, is given by p to the r 1 minus p to the n minus r into the first factor, which is n factorial over r factorial into n minus r factorial. Okay. In a similar way, this is a general term for r successes. You can actually calculate the failure of the probability of failure too, but for that your right hand side will be different. And this is what is called a binomial distribution. Is it difficult or it's fine, right? I need some
It's
feedback.
fine.
I can't see. Is it okay?
Yes, sir.
Thank you. Let's see how it looks. This is also called Bernoulli's distribution because James Bernoulli was the first to talk about this, to calculate this probability and talk about this distribution. This is also called Bernoulli's distribution. And you see, this is how it looks. You see, for each distribution of data samples, it is written P and N. So you have 4 trials, the top left corner. You have 4 trials with the probability of success 0.5. If it is so, then your distribution for 4 trials, you see the x-axis is 4. So you can have only 4 trials. If you have probability of success 0.5, you can have this distribution. Similarly, if you start moving, if you change, because n minus 5, n equal to 5, so you have 5 trials here, you can have probability 0.05, it's the same. The distribution looks like this. Then you come here, then you come here. Okay. And then for different probability and number of trials, it is like this. Out of these eight possibilities, keep in mind this, because this will come later in later discussions also. You see, the probability of success is 0.5, but n is equal to 50. Here n is equal to 4, here it is 5, here it is 15, here it is 5 again, 15 again, 5 again, 15 again. But this is 50. That means the n is very large compared to the others. So as n goes to very large, the distribution has a very distinct shape, okay, compared to the other distributions, okay. And for this, I'll give you a homework that the properties of the binomial distributions can be described like this. So the mean of this distribution is n into p. N is the number of trial, p is the probability of success, and the sigma, that is the variance, is given by square root n into p into 1 minus p. Okay. So these two properties define a binomial distribution. And the homework is you prove this. Okay. That prove that the mean of a binomial distribution is equal to n into p. Sigma of a binomial distribution is n into p into 1 minus p. Okay. Just do a small calculation, you get it. I hope all of you will get it. If not, we can come back later. Okay. So this is what is a binomial distribution. So binomial distribution is a distribution that talks about if you have only 2 outcomes of an event. Okay. If you have different outcomes, then it does not help you. But if you have only two outcomes, success and failure, pass or fail, goal or no goal, something like that, head or tail, you can take help of binomial distribution. The next is, okay, there's an example also. You are trying to detect tracks of cosmic ray particles, use plastic scintillators. Okay, very nice. Each of which is 95% efficient. So you require at least 3 points to record a track, right? You have a stack of 3 flat plastic scintillators. So you can a stack of I say that this is a plate of plastic scintillators. Just put one after the other vertically stacked. So at least, okay, 3 points are needed to record a track. Of course, 2 points is not a track. 3 points, you define your track to be at least 3 points. What will be the track finding efficiency of a stack of 3 detectors? Can anybody tell? Each detector is 95% efficient. If you require at least 3 points, 1 point in each detector, so what will be the track finding efficiency if you have 3 detectors? You have 3 detectors, and if you want, each of these 3 should give 1 point so that you can get a track. So what is the track finding efficiency in this case?
Cube of 0.95.
Sorry?
Cube of 0.95.
I don't get you. So, in the chat box, maybe your voice is not. Who is this?
Sir, Ashwini from Isaac.
I can't hear you. I don't know whether it happens to me or it is for everybody. Can you write in the chat box? And what is the answer? Let me see. I can't see the chat. 85. Question is says 0.95 cubed. Okay. And what would be the improvement if you use 5 such detectors? But your requirement is still 3 points. You need 3 points to get a track. So what would be the improvement in the track finding efficiency if you use 5 detectors, but you still require 3 points to get a track? Ashwini? Anybody else?
Multiplied by 5C3.
Who said that?
Rakesh Nayak, sir.
Rakesh?
Yes, sir.
Okay. Let's see how it goes. You see, you need 3 points, right? That is what is your R value. And this value is 0.93, and then you have 3 detectors, so you can have 3 only, right? So then you put these values in your distribution, which we discussed in the last slide. Then you get this 85.7%. What happens if you have 5 chambers? Then you can have, you still ask for 3, but you can have 5 here. Okay, you can have 4 here, you can have 5 here. Okay, then you have the probability goes like this. For some similar calculation, you put these values and you get these probabilities, which happens to be 99.9%. Okay, so with the 5 detector stack, you can get it like this. Okay, so very good. What happens if you do not have any idea about the number of trials? Okay, we have already come to the Poisson distribution, and the question is, what happens if you do not have any idea about the number of trials n? You do not know what your n is. When it can happen like that? For example, a GM counter, you have a radioactive source and you have a GM counter sitting next to it. It gives a signal when there is a decay. But if there is no decay, there is no signal, right? In case of a coin, it was you toss it, it is either head or tail. You kick a ball to the goal from the penalty spot, you either get a goal or not. But here it is not like that. If there is a decay, there is a signal in your counter. If there is no decay, there is no signal. So you don't know actually how many trials are there, right? No decay. You can have no decay for a long time and then one decay. So you get a signal, but that does not mean, so for example, at 1 second you get a signal. That does not mean that in next 5 or 4 or 10 seconds, when you will get a signal. You cannot tell it like that, because you do not know how many trials. You are not trying at all here. So if you try it and you have a probability of getting one or the either, this is not the case like that. Okay. So in one instance of decay does not affect the probability of time of the next decay. You do not know when the next decay will happen. If you get a signal, that does not tell you anything about the next decay. Okay. So the probabilities are independent. But the average number of signals. So if you really wait for a long time, then the average number of signals within a given time interval, for example, 10 seconds, is usually same for different time intervals. So if you wait for 10 seconds for a radioactive signal, unless you measure it today and measure it 10 years after that, when the half-life of the material has, the number of decay, number of nuclei available is less, that's a different issue. We are not discussing. But today, if you measure for 10 seconds now, and then another 10 seconds, and another 10 seconds, and another 10 seconds, for this 10 seconds interval, you get a number of decay signals. And the average number of decay signals for all these 10-second intervals are usually the same. So for this case, we take help of Poissonian distribution. So the Poissonian distribution gives the probability of a given number of events occurring in a fixed interval of time or space if these events occur with a known constant mean rate and independently of the time since last event. So by known constant mean rate, I mean that the decay in 10 seconds, this 10 seconds is similar or same for the next 10 seconds and next 10 seconds, like that, and independently of the time since the last event. I mean, you do not know when the last decay has happened, and if a decay has happened, you cannot predict the next decay. They are independent. So this is known from once again the discoverer of this distribution, Simeon Denis Poisson, and he is the same Poisson who gave you Poisson bracket, Poisson distribution, Poisson constant. It's the same Poisson. Suppose that on an average, lambda number of events are expected to happen in some interval. You know that for 10 seconds, you can have these many decays. So on an average, lambda number of events are expected to happen in some interval. You know that. If we split the interval in n very small equal sections, okay, so that the chance of getting 2 events in one section is negligible. Your interval is not so wide is sufficiently narrow that the chance of getting two events in one section, it does not happen, then the probability that a particular section contains an event is lambda over n, right? You can have lambda, you have lambda number of events, you have n number of intervals, and you have made this interval in such a way that the probability of getting two events in one interval is negligible. So the probability that a particular section contains an event is p is equal to lambda over n. Okay. Then the probability that there will be r events in n sections is given by the Poissonian distribution, which is once again written in this way: r lambda over n, and n that is equal to lambda to the power r divided by n to the power r, 1 minus lambda divided by n minus r, n factorial, n minus r factorial. So this is coming because of p equal to lambda over n, right? It just replaced p with lambda over n. Then for finite r, if n becomes infinite, your r is finite, n becomes infinite, then your n factorial by n minus r factorial goes like this. Okay, and you can actually calculate and see that this is actually n to the power r. You can do this, you have done this, I guess, when you did your permutation combination course in class 12. And the second factor, 1 minus lambda over n to the power n minus r, goes to 1 minus lambda over n to the power n, which is like this. Okay. With these two limits, the binomial distribution leads to Poisson distribution, which is given by p r lambda e to the power minus, sorry, this is e to the power minus lambda. E to the power minus lambda, lambda to the power r by r factorial. Okay, this is lambda to the power r. This is e to the power minus lambda, and this is n to the power r, and n to the power r into the power r cancels out, and then n is infinite, and you get e to the power minus lambda, lambda to the power r divided by r to the power r factorial. So that is what is Poisson's distribution, and that distribution deals with those events. Now let us have a look at how it looks like. It looks like this distributions, and you see here you have only one thing, that is lambda, that varies. So you have once again r can be up to 5, up to 25, up to 80, whatever, you don't care. Your lambda changes. As your lambda changes, your distribution changes. Here the lambda is 0.1, lambda is 0.5, lambda is 1, lambda is 2, lambda is 5, lambda is 10, and you see lambda is 50 here. Okay, lambda is 50. So if you have very many number of sections, then this curve becomes like this. Okay, if you have larger lambda, you have a more smoother distribution like this. And once again, like the binomial thing I told you, keep a look, keep an eye of over the distribution. Here also I'll tell you that if you keep an eye over this distribution where lambda is very high compared to this. Okay, this also has properties. The Poissonian distribution has properties, like the total probability is given by this. The mean number of events is given by this, as we discussed, and the standard deviation of this distribution sigma is given by square root of lambda. Okay. Once again, I would like to tell you that you prove these relations or properties by yourself. Okay. Do that yourself. This is not very difficult to get this. I'm not discussing this, but these are the properties that defines Poissonian distribution. What happens when two events both following Poissonian distribution occur. You have two events, both of them are Poissonian. What happens? For example, there is a radioactive source which contains two different unstable isotopes. So there is one source, but one source may contain two different isotopes. And these two different isotopes, each of them will follow Poissonian events as we discussed. So there is a source which has two Poissonian distribution, which has two isotopes, which is a source of Poisson. Each of them is a source of Poissonian events. Two event types, A and B, with individual means. So both of these events have, each of them has a mean, which is lambda A and lambda B respectively. So for a total number of R events, there will be RA of type A and definitely R minus RA of type B. Okay, then the probability of R will be given by probability of RA and probability of R minus RA, right? So it's actually B, but B is equal to R minus RA. Then this, if you take the product of these two property, these two probabilities, you get the total probability for any event. You know that this will happen. A little algebra, if you put these values, then it leads to this. Once again, I think you'll be able to go from here to there, but if not, then in the next class you can ask me, we can discuss how you have to go there. But this is what happens if you take the product of two Poissonians. You see what it is? Your mean is the sum of two means, right? That is the most important thing. The sum of two Poissonian processes is another Poissonian process. So this expression exactly look like your, so the Poissonian distribution was e to the minus lambda, lambda to the r by r factorial. Here it is the same, right? Only thing is your lambda is now a sum of two different processes. So if you have two Poissonian processes, the sum of these or the total probability from this is once again Poisson. So you don't have to worry about it. Okay. As I said, that you prove this, that how you come from this PR, this expression to the equation number 30, that the sum of two Poissonian processes is another Poissonian process. Okay. Oops, something like that. Okay. So let's move. And this is what we are all waiting for. This we hear all the time. That is, this is a Gaussian distribution, and this is definitely the most popular one, which has two parameters. One is a mean and the sigma, and it is defined by 1 over sigma to the power square root of 2 pi exponential this. And the distribution is a bell-shaped continuous distribution. This is, as I was telling, that the binomial and the Poissonian are discrete distribution. You see, for binomial, you had two different results. So you can count it, and for decay also you can count it. So those are discrete. Okay, but Gaussian distribution is a continuous distribution centered on and symmetric around mu. This is the mean. The distribution is symmetric. You remember that we said that the skew and kurtosis, they measure the shape of the distributions, and kurtosis, the skew also is 0 for a Gaussian distribution, so it is symmetric. Kurtosis is also 0 for the Gaussian distribution, and kurtosis is actually not a measure of symmetry. It is a measure. It is tuned to Gaussian, and if kurtosis is 0 for a distribution, that is Gaussian, or rather the other way, kurtosis is 0 for a Gaussian distribution. Width of this distribution is controlled only by the parameter sigma, which is the standard deviation, and at x equal to plus and minus sigma, your px, which is the height of this, falls to 0.1. 0.61, okay, not 0.5. You remember that FWHM, which is right at the middle, was 2.35 into sigma, okay, and that is why it is the same thing, that at sigma it falls to 0.6, not 0.5, okay. So by substituting this, if you substitute this with a standardized variable like z equal to x minus mu divided by sigma, then you get this, okay. So sometimes, so you can substitute this with this, and then you get a simplified simplified equation, which is this. It depends on z only. So that means your mu here is inside the z, okay. And this is called an unit Gaussian distribution or unit normal distribution. But once again, we all call Gaussian distribution a normal distribution. But just keep in mind, there is nothing abnormal about Poisson and binomial. Okay. So this is normal in the sense that it is symmetric around the mean. That's exactly why, and that is only why it is called a normal distribution. It does not have a skewness. It does not have a. It is symmetric. It does not have a kurtosis. I mean, the kurtosis is defined with respect to the Gaussian. So only because of this, it is called a normal distribution. This has nothing to do with any abnormality related to other distributions. Okay. So it is better to call it Gaussian rather normal. Okay. So it has also, like for other distributions, it has properties like the total probability is always 1. You all know. The mean is this, and the variance is this. Once again, I would urge you to prove these relations, these properties. However, there's a note, as I say, although this is named after Gauss, we all know that it is Gaussian. It was independently discovered by many others, including Laplace. In fact, the first recorded reference to it is by de Moivre. And there are others we just quoted because we know these names. They are also famous for other. Am I connected? Hello?
Yes, sir.
Okay. I just got a notice that my internet connection is unstable, so I just made sure. So I just quoted these two names because we all know these names. There are many other people who actually did this. And why it is called Gaussian, because you see that the first recorded reference to it is by de Moivre. And as I explained, it is many times called normal, but however, it is best avoided because this normal, I mean, somebody can ask, so that means, are the binomial and Poisson abnormal? No, it's not like that. It's just normal because it does not have a skewness, it is symmetric, it looks nice, that is why it is normal. Okay. And it describes many different sorts of data, particularly in context to measurement of errors, which we will move on to the next section of the lecture starting on the next day. But the reason for this, why the errors are Gaussian, is not very simple to explain. And this will be beyond the scope of this discussion. This is a result. We know that they are Gaussian, but why they are Gaussian is not so simple to explain. Okay. And we discussed three distributions, and there is relation among the distributions. What is this? Binomial and Poisson. Let's see what is the relation between them. When n is large and the probability p of the occurrence of an event is close to 0, then q becomes 1 minus p is 1 because p is 0, and the event is termed as a rare event because you always get success, right? Sorry, you not very often get success. The p is very small, p is very close to 0. So it's a rare event. In such a case, a binomial distribution could be approximated by Poisson distribution with lambda equal to NP. Okay. This is the relation between binomial and Poisson. Binomial and Gaussian. Gaussian distribution is an approximation of binomial distribution with mu equal to NP and sigma equal to square root of NPQ. When number of possible observations n becomes infinitely large. Now, do you remember I told you that you keep in mind the binomial distribution with n equal to 50 that looked like Gaussian, right? This is why it is. The infinitely large and the probability of success in such case such that NP is much greater than 1. So in that picture, it was the probability of success P was 0.5, N was 50. So NP was much larger than 1, and it looked like Gaussian. This is exactly because of this. And there's also a relation between Poisson and Gaussian. The Poisson distribution approaches Gaussian distribution with a standardized variable z if lambda goes to infinity. In that case, this becomes the Poisson distribution approaches a Gaussian distribution.